Doug Batchelor mentions in one of his videos the problems with the fossil record and the radiometric dating methods. His main concerns are how the fossils and the rock around them are being dated, and I would like to give him a short summary of that. As an easy example, we have the carbon-14 dating method. All living things contain carbon, and this carbon is a mix of different isotopes of carbon atoms. Carbon-12 consists of 6 protons and 6 neutrons, and carbon-13 consists of 6 protons and 7 neutrons. These two are stable, which means that the nucleus of the atom won't break naturally. So when a living thing dies and becomes fossilized, these carbon atoms will remain the same in number. But ordinary carbon also consists of carbon-14. This isotope is unstable and will decay into a different atom over time, more precisely nitrogen-14. So to measure the age of something containing carbon-14, we need to look and compare the amounts of carbon-14 and nitrogen-14 in the sample. If, for example, the amounts are equal, half of the carbon is decayed into nitrogen, which means that one half-life has passed. When talking about carbon-14 decay, the half-life is 5,730 years. This is how radiometric dating works. And to further give a response to the people that need to watch things happen to believe it, there are elements in the periodic table that have much shorter half-lives, and it is therefore possible to analyze this process whilst seeing it happen. Carbon-11, for example, has a half-life of 20 minutes, so this is an established dating method. What is important to remember, though, is that when enough half-lives have passed, the amount of the parent isotope will be so small that a secure measurement of time can't be made. For carbon-14, for example, this limit is around 40 to 70,000 years, depending on the size of the sample. To further describe this, when the 9 half-lives have passed, after about 52,000 years, 0.2% of the original carbon-14 will be left in the sample. And then after 10 half-lives, or almost 60,000 years, 0.1% will remain. This amount is so small that secure measurements can't be made because the two quantities are so similar, but the age difference is huge. This continues and becomes harder for older samples. A good way to put it would be to compare the percentage difference from the original sample to the year difference, because what's important is a big time span which is more secure to work with. In the first half-life, there's about 115 years for each percentage point, but in the second, there's twice as many years, 230 for each percentage point. For each increasing half-life, the ability to put a perfect year match decreased by half. When a high enough half-life is reached, there will be almost no difference of a 1,000,000-year-old sample and one that's only, for example, 60,000 years. If this is not remembered, and that goes for all the different elements and their limits, wrong conclusions could be made from the results. This is something that a lot of creationists seem to overlook, and instead bring up arguments where they've measured the age of carbon life forms in much older samples. A good example of this is Ken Ham in the recent debate against Bill Nye, where Ham tries to falsify radiometric dating methods. He tells the audience about an excavation to a basalt layer deep underground, where the radiometric method of potassium-argon dating was used. This is a common method of radiometric dating, since potassium has a very long half-life, almost about 125 million years, which makes it easy to put a certain age on the sample, since not many half-lives will pass for a long time. But according to Ham, this basalt layer was dated to 45 million years. What he then goes on to say is that wood was found inside the basalt layer and sent to the same lab, but analyzed with the carbon-14 dating method and dated to 45,000 years. As mentioned before, there is no possible way to examine a sample of greater age than about 70,000 years with the carbon-14 method. Since the difference will be so small, it can't be securely translated into years. Doing that will give a year that is close to the year limit of that radiometric decay. Therefore, it is important to know how radiometric dating works before attempting to analyze the results. Ham gives more critique to this method by saying that we don't know if there were daughter isotopes in the sample from the beginning. I would like to respond to that by giving an example from the potassium-argon method. Argon is a gas that doesn't react with minerals, which means that there will be no argon gas in the mineral when it's formed. But if there's potassium trapped inside the mineral, which decays into argon, the argon will then be trapped inside the mineral, like the potassium was. We can then observe the amount of argon and compare it to the amount of potassium and give an answer to the age of the rock. Radiometric dating is a functional method for measuring age, but people need to know exactly how it works before trying to analyze the results. Leave that for the scientists to do, not the preachers.